You help to move a 51 kilogram bookcase to a different place in the living room. You're going to push the bookcase with a force of 65 newtons, and it's going to accelerate at 0.15 meters per second squared. We want to know the coefficient of friction between the bookcase and the carpet. All right, suggestion is let's first list all the variables present. Okay, so let's just start from the beginning. 51 kilograms, so that's our mass, right? So 51 kilograms is M. Then we are pushing with a force of 65 newtons, so there's going to be a force that we apply. I'll put a P for pushing, 65 newtons. And then the bookcase is going to accelerate at 0.15 meters per second squared. And that's everything we know. And it's asking us what is the coefficient of kinetic friction, which is mu k. Okay. So after we list our variables, let's do a free body diagram. So the free body diagram is going to be for the bookcase. So we know gravity pulls down, so that's Fg, which is mg. So that's going to be 51 times 9.8. So that's 500 newtons is what it comes to. And then we know the normal force is going to match that. So the normal force will also be 500 newtons. Now, the bookcase has a positive acceleration to the right. So let's put our pushing force to the right. That's 65 newtons. And then we know there's going to be friction, but it's going to be a smaller arrow, right? Because to have an acceleration, you have to have unbalanced forces. So there needs to be more force that way than this way. So the force of kinetic friction will be less than that. So we're going to solve for that and then work towards mu k. Because remember, our equation for mu k is force of kinetic friction is mu k Fn. So to get mu k, we got to have the kinetic friction force and the normal force. We already have the normal force. So if we get kinetic friction, we can solve for mu k. So in chapter 4, the procedure was always free body diagram, Newton's second law. So our free body diagram is as complete as we could be. Let's do Newton's second law. So F equals ma. Now, the y forces are balanced, right? Gravity and the normal force are balanced. So there's no acceleration in the y direction. It's only in the x direction. So pretty much for the rest of the year, we're going to be treating x and y separate. So when I write Newton's second law here, all I want to do is look at what forces are in the plane of the acceleration, so in the x direction. Two forces, Fp and the force of kinetic friction. So force pushing plus force of kinetic friction equals the mass of the bookcase times its acceleration. So we have 65 plus kinetic friction equals the mass of the bookcase, 51, times its acceleration, 0.15. And now you multiply these, and then you bring over your 65, and you get the force of kinetic friction is negative 57 newtons. So now we know this is 57 to the left. Just as we expected, it's lower than the pushing force because the acceleration is to the right. And now you have your friction force and your normal force, and you need both of those to get mu k. So let's plug them in. 57 equals mu k times 500. And then you solve for mu k, get 0.11 is your answer. And you'll notice I drop the sign when I'm solving for mu k because this is not a vector. The sign doesn't matter. We're just finding what portion or what percentage of the normal force is the friction force. All right, let's go. So the mass of the book, 2.25 kilograms. The acceleration, 3 meters per second squared. That's once it gets going. The coefficient of kinetic friction, 0.250. Coefficient of static friction, 0.340, and those are our variables. Now part A says how much force do you need to start the book from rest. Remember we talked about static friction yesterday. Static means stationary, so that's this friction that's present when you're trying to get an object moving and it won't move. That means that static friction is matching your applied force. So for part A, let's look at a free body diagram for the book before it moves, before we even push it. Fg is down. That's 2.25 times 9.80. Does anybody have that? 22? 22 newtons. That means your normal force is 22 newtons. Okay. That determines how much friction you can have, right? The amount of normal force. Now, so I start pushing on the book, it's not moving. That means static friction is matching it. Static friction, this tells us it can go from 0 to a maximum value where mu s Fn will give that maximum value. So when I'm not pushing on it, static friction 0. I start pushing, it's not moving, static friction is beginning to climb, to increase. Eventually I push with enough force that I get it moving. That force that gets it moving, the pushing force, will be just a little bit above my maximum static friction. So if we solve for the maximum static friction, then we know how much pushing force we need to apply. So the maximum static friction is found by setting FFS equal to mu s Fn. That'll give us the maximum. So then we do 0.340, which is the coefficient of static friction, times 22 newtons. And you said it was what, 7.2? 7.5. So we get 7.5 newtons. So that is the maximum static friction the surface can provide. Therefore, we're going to say that's how much force I need to apply in order to get it moving. So that's all you had to do for A. Now part B, the book is going to accelerate at 3 meters per second squared. So let's first look at a free body diagram for the book when it's accelerating. Fg is still the same, 22 newtons, and the normal force is still the same, 22 newtons. Now we know we're going to push it this way, and that it's going to accelerate to the right at 3 meters per second squared. Therefore, this arrow is going to be longer than this arrow, just like the bookcase problem, because we have an acceleration to the right. And this is what we want to find is how much of this force do we need here. Looking at just the forces in the x direction, we don't know either right now. We want this one, so we're going to need to use Newton's second law because we have the acceleration, we have the mass, so we got to be able to find this one another way. So we have our equation that we've been learning in chapter 5. The kinetic friction force is equal to the kinetic coefficient times the normal force. So that's going to be 0.25 times 22. And when you solve for your friction force, you get 5.5 newtons. So now we know this friction is 5.5 newtons. So that's chapter 5 stuff. That let us find this unknown force. Now, free body diagram, let's go to Newton's second law, F equals ma. Looking at only what's going on in the x direction. So you have Fp plus kinetic friction equals ma. So Fp plus, now this is going to be to the left, so it's negative 5.5 equals the mass of the book, 2.25 times the acceleration, 3. And then we solve for the pushing force, and we get 12.2 newtons. So that is the answer for how hard you have to push. Any questions on anything up to this point? Okay. Part C is asking us, what should the coefficient be to keep it moving at a constant velocity given an applied force equal to part B. So that's the applied force. So for part C, free body diagram will be gravity down, 22 newtons. Normal force up, 22 newtons. Now it tells us we want to apply the same force from part B, which was 12.2 newtons. And to move at a constant velocity, we know that the kinetic friction needs to match that. So now we have kinetic friction, we have normal force, so we can solve for what the new coefficient would be. So you have 12.2 equals mu k times 22. And so then mu k is 0.55. And that's your answer. And notice we aren't putting signs when we're calculating the coefficient because it's not a vector. We just need to know the magnitude of the forces.